Let's start with an uncomfortable truth that most attention-grabbing headlines deliberately avoid. Diamond nuclear batteries can't even provide energy for your car's dashboard, let alone move the vehicle. Not today, not in 10 years, and not ever. That fact alone is enough to shock you. Because if a battery is claimed to last for thousands of years, why can't it operate a car for even 1 kilometer? If nuclear energy is so powerful, why are automakers still obsessed with lithium-sodium and solid-state batteries instead of aiming for these eternal nuclear batteries? The answer is extremely simple, and it is utterly shameful for the marketing machine. Diamond nuclear batteries have almost no power. I'm not saying less powerful. I am saying they are many times weaker, to the point that the idea of using them in electric vehicles collapses under basic electrical engineering math. The first problem is the confusion between energy density and power density. Imagine this. I give you a reservoir full of gasoline, enough energy for you to drive around the Earth 100 times. But there is one condition. You are only allowed to extract the fuel using a straw as thin as a hair. Do you possess the quantity? Yes. But will your car move even 1 centimeter when the amount of gasoline trickling into the engine is measured in drops? That is exactly the tragedy of the beta-voltaic diamond nuclear battery. In essence, this technology collects electrons shot out from the natural decay process of the carbon-14 isotope. This is a random process, and most importantly, it is extremely slow. You cannot step on the gas to make the atomic radioactive decay happen faster. To operate a small electric vehicle like a Tesla Model 3 at highway speeds, you need a continuous energy flow of about 20 kilowatts. When accelerating, that number increases to 200 kilowatts or more. So how much does the most modern diamond battery cell in the lab provide? Only about 100 microwatts per cubic centimeter. Can you visualize this discrepancy? 1 watt equals 1 million microwatts. To have enough power just for the car to crawl on the road, you need 200 million such battery units. If we perform a physical volume conversion calculation to create engine power equivalent to a normal car, your diamond battery block would have to be about 1,500 to 2,000 cubic meters in size. Are you ready to drive a car that has to tow a miniature 5-story apartment building behind it just to hold the battery? The mass of that battery would be so great that the car would sink deep into the ground the moment the wheels touch the road. So where does the promise of a compact battery fitting in the car come from? That is a lie regarding physical scale. But let's assume, just hypothetically, we find a way to compress billions of layers of nano-diamond and radioactive material together to shrink the size down to that of a current lithium-ion battery pack. At this point, we will slam into the second wall, thermodynamics, and the problem of self-absorption. When you stack radioactive materials too densely, the beta particles shooting from the inside cannot escape to the outside to create electricity. Instead, they crash into the neighboring material layers themselves. And when that kinetic energy is blocked, what does it turn into? Heat. A massive amount of heat. The conversion efficiency of current beta-voltaic technology reaches under 10%. This means more than 90% of the energy will turn into thermal energy. If you try to force a compact block of radioactive material to generate 200 kilowatts of electricity for acceleration, it means you are creating nearly 2 megawatts of heat right underneath your seat. Would you sit on a chair lined with 1,500 industrial heaters turned on at full power? No cooling system on a personal car can handle that amount of heat without turning the car into a hot reactor. The car would vaporize before you met the output requirement. And finally, let's talk about money, the most realistic language. Supporters of this technology often say, technology will get cheaper over time. True, but the limits on raw materials cannot be broken. Carbon-14 must be extracted and manufactured from nuclear reactor waste, a dangerous and expensive process. Synthetic diamond used for semiconductors is not the cheap kind used for industrial drill bits. Currently, the cost to create 1 watt of electricity from this technology falls around several $million. Please perform a ruthless comparison. A lithium-ion battery pack for EVs today costs about $100 per kilowatt hour. And diamond batteries. To have a pack capable of running the price to pay would be compatible with the national budget of a small country. Is anyone crazy enough to spend billions of dollars for a Toyota Camry just to save a few dollars on charging each month? The economic math here is not just faulty, It is absurd to the point of being laughable. So why does the media still hype it? Why do million-view videos still appear? Because it hits the lazy mind and the human desire for eternal convenience, selling a beautiful dream but hiding the technical reality. Diamond nuclear batteries are a real and wonderful technology, but their place is in pacemakers, in sensors deep under the ocean floor, or on spacecraft flying out of the solar system places that only need a few microwatts of electricity, and cost is not an issue. As for electric vehicles where high-power fast discharge capability and reasonable cost are needed, diamond batteries are forever an outsider. Don't let flashy render images blind you to the unchangeable laws of physics.